Hello and welcome. When you choose an oscilloscope, the very first specification you look at is almost always the bandwidth. But what exactly is bandwidth, and why is it so critical? Today, we'll define oscilloscope bandwidth and show you how to choose the right amount for your digital and analog projects. Oscilloscope bandwidth is defined as the lowest frequency at which an input sine wave signal is attenuated by 3 decibels, dB. This might sound technical, but practically, minus 3 dB of attenuation translates into approximately a 30% error in the measured signal amplitude. This is why you can't make accurate measurements on signals that have significant frequency components near the scope's bandwidth. Oscilloscopes generally have one of two frequency responses. Scopes with lower bandwidths, usually 1 GHz and below, exhibit a Gaussian response, which has a slow roll-off. Higher bandwidth scopes, typically above 1 GHz, use a maximally flat response, which is flatter in the passband and has a sharper roll-off near the bandwidth frequency. Maximally flat responses offer more accurate measurements on signals within the bandwidth. Also, note the relationship between bandwidth and rise time. For Gaussian scopes, it's about 0.35 divided by the bandwidth. Let's move to digital applications. The easiest but least precise guideline is the rule of thumb. Your scope's bandwidth should be at least 5 times the fastest digital clock rate in your system. This ensures you capture the fundamental signal and its first 4 harmonics, which are crucial for accurately representing the overall signal shape. For instance, a 100 MHz clock requires at least a 500 MHz scope. If you need accurate measurements on high-speed edges, you need a more precise method that accounts for the fastest edge speeds. The maximum practical frequency component, known as the knee frequency f_knee, is based on the rise and fall times, not the clock rate. You first determine the fastest rise time from your device specifications. Then, calculate knee frequency using 0.5 divided by the rise time for a 10% to 90% measurement, or 0.4 divided by the rise time for a 20% to 80% measurement. Finally, you use a multiplying factor to calculate the required scope bandwidth based on your desired accuracy. For example, if f_knee is 1 GHz, achieving 20% accuracy on a Gaussian scope requires 1 GHz of bandwidth, but 3% accuracy demands 1.9 times f_knee, or nearly 2 GHz. Consider a 100 MHz clock with a very fast 500 ps edge speed. A 500 MHz scope captures the square shape, but measures the rise time at approximately 800 ps, which is inaccurate. The scope is measuring closer to its own limitation, not the signal's true speed. To get a measurement with greater than 3% accuracy on this 500 ps signal, you actually need a 2 GHz scope. With 2 GHz of bandwidth, the measurement is about 520 ps, which is a very accurate representation. The clock rule alone is insufficient for high-speed edge analysis. For analog applications, such as modulated RF, the old rule of thumb still applies. The recommendation is to select a scope with a bandwidth at least 3 times higher than the maximum analog frequency of your design. This 3x factor is used to ensure you are operating in the lower part of the scope's frequency band, where attenuation is minimal, ideally close to 0 dB. However, this is only reliable if your chosen oscilloscope has a relatively flat frequency response in this low-frequency range. To summarize, for digital signals, use the 5x clock rate rule for general viewing, but rely on the more accurate knee frequency calculation for precise edge speed measurements. For analog signals, the 3x rule applies, provided your scope has a flat enough frequency response. Finally, when selecting a scope, remember to think about tomorrow's applications. If your budget allows, buying a little extra bandwidth today can save you from costly upgrades in the future.